Okay, everybody, this is Marty, and we're going to pick up with a 9-channel simulation workflow with Lark. We just went through a 3-channel, and the 9-channel is going to be very similar. We're going to be able to skip the prep component, as that'll be the same in terms of calculating the global horizontal. The materials is where we'll begin down here, and when we basically, we're going to be tripling the definition of the materials. There will be 3 instead of 1 for every type. And then when we simulate, you can see that this is tripled from the 3-channel. So for each major bin, so let's say if we have B1, B2, B3 will be this first run. The second run will be G1, G2, G3. And then the third will be R1, R2, R3. Whereas before up here we had just RGB all in one run. We're going to need 3 runs to do 9 channels. And then ultimately we'll come back and be able to post-process those with the Lucas, Ray, and photopic metrics using this 9-channel component. So let's just jump right into the material. And similar to what we were doing before, I think, yeah, so we're going to do Macbeth 15, so I set one file path, and in this case I'm going to use the 15 with the red wall. The source interval is going to be the same at 5 nanometers. The name, Macbeth 15, and then material types, so for this one it's going to be plastic, so it's a 1. But channel type, whereas before we had this set to 0, we're now setting this to 1 so that it's for 9 channels. And whereas before, so here we have 9 outputs, whereas it was 3 before. And interestingly enough, if you look at what we're seeing here, you're seeing from beginning with the blue part of the spectrum, going to the green, and then finishing with the red. So, and this is opposite from the RGB. We're really going BGR, but really B1, B2, B3, all the way down to R1, R2, R3. But if you look at the red component, if we go back to our 3-channel, just for an example, and we look at what was coming out of the channel output, we had 0.619 just for the red channel, right? So now we're getting a bit more information, a little more fidelity, and just that bit is now turned into these three different channels for that one. Okay. And that will become more important when we get into electric lighting eventually, depending on how spiky the spectral information is coming out of a source. We deal with daylight, which is very consistent across the full spectrum. So 3-channel simulations you can get away with those, whereas depending on your source, 3 channels not going to be that accurate. Okay, so this is outputting 3 different file paths, an A and a B and a C, and then these are reading those file paths, and you can see this is going to be in the B range, and this one is the G range, and this one is the red. So you can see the 4.22 all the way to the 0.718 is those last few numbers for the reds in the spectrum. Okay, so that's a plastic, and same idea with glazing. I'm using the same Madison, 4th and Madison glazing definition. Here's our name. The only big difference here again is we're setting the channel type to 1. So that's going to that'll correlate with a 9-channel. And if I move this in real time to 0, you'll see it just drops right off to the 3-channel, and then it comes back to the 1. So this is running the transmissivities on these values. So if I were to compare this 0.453 to, well, actually, if I did this, where this material type is now set to 0 for glass, if I set this to 1, you're going to see these numbers all drop. And if I set it back to 0, you're going to see them all increase, and that's a function of the transmissivity. So here we can also see their file paths and read their definitions. For the sky, let's see, same idea. We start, sorry, I'm jumping around a lot here. We start with the daylight series, and we're using, we're going to stick to the same, the 5000 CCT sky. So we're using a source daylight series cal. So because of that, we're going to set this to true, which is going to normalize the data and automatically set it to the source interval to 10. I'm just kind of double dipping here, but it should work even if we disconnected that. As for a sky, we don't need the material name, roughness, or specularity, but the type 2 is for sky if I hover over type. So 2 is good. And then channel is 1 again for 9Channel. So that's going to output our 9 channels of color, and we feed that into our sky component, and we're reading the same information out of the Ladybug EPW file and location data to get our longitude, time zone. We don't need direct or diffuse, but we are going to use the global illuminance, which is being generated live. And now that we're ready, we're going to run it, and that is automatically going to output our sky name and our diffuse and direct from the Rendell, and then it's going to generate these materials. So all of this is then going to be parsed and split into like we discussed before, the kind of A, B, and C of the spectrum. So I will focus on B, as we have, we're using B as kind of the central location to set the quality and the simulation information for, as we did before, the luminance, Honeybee recipe, and the illuminance. So this is all the same in terms of how we do this, and all the settings are going to be the same as the three channel. We are using a similar logic for the file name, except for this we have this root of B or A or C depending on which one we're running. And similarly, the sky, and actually I failed to mention that, is when we're generating these names, you can see down here there's a little A and a little B and a little C that's being appended to the name, and that's basically organizing for the 3 channels which one is which. And so the A material or sky would go up here, B down here, and then C. Okay, so we can see that those materials are live. So here's our Macbeth 15B, our glass is the B, and the sky is the B. So we're good to go. We're keeping the quality low just to run it fast, and we're going to go ahead and do this. And this is going to run everything. The Boolean is set to all the illuminance files and luminance, so it's going to take a few seconds here. And it's going to populate it into the Sea Lark metrics red, but you can set your folder as you wish. And when this is done, so what's going to happen now is similar to before, where we have these HDR output file names or file paths for the res and the HDR. That's all going to feed now into the last bit, which is the 9-channel metrics. So in this case, though, where we had 1 picture and 1 irradiance, now we have 3. And that correlates kind of in the order of A, B, C, or picture 1 would be the B's, picture 2 is the G's, and picture 3 is the R's, and same with the irradiance. So these file paths are going to be in that order of A, and then the B, and then the C. So once we have all that set, we can also create a file path that we like, or a directory, and then we're going to run this. And it's similar to before, it's just now it's tripling the fidelity, and it's going to actually combine it into one super image. Okay, so you can see here we've got the output, and so we have our this should actually be, so this is going to be our ray output, this is our Lucas output, and then we've got our photopic, and this is for both views, the looking north and looking west. And you know, you can see there's definitely some differences in those values, but we want to understand them more by looking at these various file paths to HDR images. So we're going to use HDR scope again to take a look at these. So we're going to go back to this red folder that I created, and we'll look at Lucas. And we're going to look at the false color, and we'll use a similar range of 1001 that we used for the 3-channel. Okay, and then we're going to simultaneously open up a photopic. Now, one difference here in when we're doing the 9-channel is that, so you're going to see there's Lucas 9, photopic 9, photopic 9 to 3, and then circadian 9. So there's something slightly different about this photopic 9 to 3 is that it will actually maintain the color data, which is nice. So when we look at this, we can see that, oh, there's that Macbeth 15. It's rendered as red, and this is a great way to both have a tone mapped image and a that's based on 9 channels. Okay, so we're going to we're going to edit, tools, false color. We'll do the 1001. We'll apply. Okay, so these are the same again, and right away you can see the difference of this this surface. If I click on the back wall where we have that red wall, we're actually getting slightly less from our 3-channel. We have about 6 candelas per meter squared. And then over on the left where we have the Lucas, where you're seeing what the ganglion cell is seeing, it's just under 2 candelas per meter squared. So they're 3 times the light in the photopic range than the circadian. And that's kind of in a nutshell the way this workflow works. Now, if we also wanted to take a look at ray, I can go back and open the ray curve, and we'll see in the false color relative to the Lucas. So if I click in here, it's about 1.7, and on the other side, 1.8, 1.9. So pretty high agreement. There's certainly subtle differences, but not as dramatic a difference between the photopic and the circadian. So that's a 9-channel workflow. We'll be posting more resources and keeping you updated, but thanks for coming along for the ride.